So what we use on our graphing calculator for confidence interval for two proportions and hypothesis test for two proportions, it's going to be the same. Okay. Or sorry, it'll be a slightly different function, but the same idea. Anyway, okay, so we're going to use this example for the last two lessons, and we've seen this example before earlier on in the year. Famous study, investigators created mock identical resumes, which were sent to job placement ads in Chicago and Boston. Each resume was randomly assigned either a commonly white or commonly black name, so it's an experiment. In total, 246 out of 2,445 commonly white name resumes got a callback for their resume. 164 out of 2,445 commonly black name resumes received a callback. So right now, and we can answer this with the numbers later on, but do you suspect discrimination? Why? Like what sort of obvious stands out to you? Yeah, more white names received, or more commonly white names received a callback. Okay, but we can't prove beyond the shadow of a doubt yet. Okay, we can't prove it yet, or have convincing evidence for it yet. So we've got to do some statistical analysis. So remember when we worked, so we're going to do a confidence interval. And remember when we worked with one proportion, well, we needed to know the sample size, and we needed to know the sample proportion number. Okay, so that we could find, we needed to know how many preferred something or favored something, so we could find P1 or P hat. But now we're just going to do two proportions, and we're going to analyze the difference between them. So we've got two sets sort of information here. We're going to let P hat 1 be the proportion of commonly white names that got callbacks. P2 is the proportion of commonly black names applications that got callbacks. And we want to find N1. Well, N1 is the total number of commonly white name resumes that were sent out, which is 2,445. N2, same amount of resumes were sent out for a commonly black name. The sample proportion, remember, that's the number who received callbacks over the total sample size. So for white names, it was 246 over 2,445, which is approximately 0.101. That's the proportion of white names who received callbacks. So the percent would be 10.1%. For commonly black names, the proportion was 164 out of 2,445, which works out to approximately 0.067, or about 6.7%. So again, if we see those as percents, we can suspect discrimination. And finally, the difference between the proportion of white names and the proportion of black names that receive callbacks, we just subtract those two. Order is important. It's P hat 1 minus P hat 2. And that's going to give us approximately 0.034. Which suggests right now that about 3.4% more white names receive callbacks than black names. That's what it suggests right now. But we could have got those results by chance alone. Okay. We're not entirely sure yet. So are they different enough to show convincing evidence of discrimination? Possibly, but we don't know for sure. Because we may have got these results by chance. Because who knows, maybe if we tried it again, this would be negative, which means that more commonly black names received callbacks, right? And if we did it a third time, maybe we get a few more whites again. If we do it a fourth time, maybe we get a difference of 0, the same amount, who knows? Okay, the question is sort of how significant is this? And that's where our stats analysis comes in. Okay. So, sorry, I just want to finish this here. I can hear you all flipping. P1 minus P2 suggests discrimination. Plus, the sample size is pretty big. So that sort of aids to it as well. But again, we don't know for sure. Yeah.
Is that like a name for like what P1 minus P2?
Just the difference in sample proportions. Okay. So remember, like we did with confidence intervals when we first started, we sort of did it the long way by hand, and then we were able to do it a shorter way in a 4-step process using a graphing calculator function. So we're going to do the same thing here. But before we do that, just remember, a one sample situation, you're comparing a statistic in one population against some claim about that population. But in 2 sample situations, you measure the same statistic in 2 populations. Because a lot of times it could be an experiment. And see if they're significantly different. So just as another example, one sample, just so you have an idea. Is the proportion of brand A batteries that are faulty %5 or greater. So we take one population, brand A batteries, and then we can construct a confidence interval. And if in the confidence interval, everything is either 5% or above, then we would say, yeah. If when we got our confidence interval, we got values below 5%, then we couldn't say yes for sure. And so those are the ones we've already done. A 2 sample would be is the proportion of brand A batteries that are faulty greater than those of brand B. Now we're comparing two populations. So we find the difference from them, and we construct a confidence interval of the difference. If all the numbers in the confidence interval are positive, then we would say, yeah, okay, the proportion is greater because all the numbers in the confidence interval fall higher than 0. If any of the values are negative, we can't say, well, no, because it could be there might be ones where brand B is, those brand B batteries are more faulty. Okay, so we're going to do a confidence interval. And remember, we call it, when we do a confidence interval for proportions, we call it a Z interval. Okay. We've already done one sample Z interval, so the only difference here is we're going to do a 2 sample. And again, we need 3 pieces of information. Conditions must be satisfied. And then we can use these amounts. It's slightly different than one proportion. This is not normal. So that means that all the sample sizes times their corresponding proportions must be greater than or equal to 10. That means it's a normal distribution, and we can use normal calculations. As long as it's random, randomly assigned, randomly selected, we can say that the difference, the average difference in the sample proportions will be our sample proportions, first one minus the second one. And then the standard error, remember we call it standard error when we're doing confidence intervals, not standard deviation. Remember in the original one, we just did p hat times 1 minus p hat divided n. But because we have 2 proportions now, we have to find those of each and add them together before taking the square root. Okay? We don't subtract them, we add them. But if it's an experiment, we don't have to worry about meeting this condition because it'll already be met. So in our situation, assume normal. The average of the difference in the sample proportions will be the difference in our sample or samples when we subtracted them. Remember, it was 0.034 from the previous page. That was our sample difference. And then the standard deviation of the difference between the two. I'm going to do it below here. Will be the first sample proportion, which was 0.101 times 1 minus 0.101, divide the sample size of that first proportion, which is 2445. Sorry, I should make this a little bit more obvious. Taking the square root of the whole thing. Plus the proportion of commonly black names, or p hat 2, which was 0.067 times 1 minus 0.067 divided by 2445. And when we do these calculations, add them together and take their square roots, we're going to get a standard error of approximately 0.0079. So now that we've got the mean of all the sample proportions, the standard error, and that it's normal, we can do this. So we've got 0.034 as our mean. And then we have to add three 0.0079s to get these three notch values. And then we have to start at the mean and subtract three 0.0079s to get the three notch values below. So I'll just give you those. It's going to be 0.0419, 0.0498, and 0.0577 for the three notches to the right. And then we're going to get 0.0261, 0.0182, and 0.0103. And remember, this represents if we pulled several samples. Okay. And then found the first proportion, commonly white names, minus the second proportion, commonly black names. We would get a group of data, a group of numbers that would fall within here. Some would be down here, some would be up here. The majority would be in the middle grouping around the mean, the average of them. Okay, so we're going to have like these all contain like P1 minus P2, P1 minus P2. If we do this over and over again. We're going to have a whole bunch of different values in there. I've just put 4 in there. But remember, and then this is going to be our confidence interval, depending on our level of confidence. So we said 95%. We want to be 95% confident. How many standard deviations was it within the mean again? We learned that, I mean, we first learned that it was 2, but then we figured out, no, it's actually 1.96. So this is 1.96 standard errors to the right, and this is 1.96 standard errors to the left. And that's going to be if we want to be 95% confident. It's going to be from just past this notch here, a little bit greater, to just a little bit less than this notch. So it looks like just on inspection first, we're going to be about 0.018, a little bit higher, or 0.019 maybe, somewhere around there. All the way up to, well, 0.0496 or 2, or maybe 0.048 if it's a little bit less, okay? But if you notice something, all the differences are positive. So that's going to actually tell us a conclusion that we'll talk about later. Okay. Well, let's get these numbers exactly. And remember to get these numbers exactly. Remember to find the confidence interval. It's the statistic or the point estimate. Plus or minus the what we call the standard error, sorry, the Z score times the standard error of the difference between the two. And remember, that actually represents the margin of error. It's made up of the number of standard errors times the actual standard error above and below the point estimate. So we got 0.034 plus or minus, and we said 95% is 1.96 standard errors away, times the standard error itself of 0.079 gives us a confidence interval of 0.018516, if I want to be as precise as possible. You can round again, like we talked about before. I mean, if you want to go 0.019, that's fine. To 0.049484. And again, if you want to go 0.049, that's fine too. So those are the value, that's the lowest value on the 95% area on the previous page. That's the high value. So just to add to this here, where that is 0.018516. That's the lower end of the 95% area. The upper end is 0.07. So again, that's constructing it by longhand, quote unquote. And then interpreting the interval. Well, we should be pretty familiar with this now. We are 95% confident the interval, and then however you want to round it to, or if you want to just write the numbers exactly, 0.018516 to 0.049484. Yeah. Oh, because I was looking at that. Thank you. Yeah, that's the upper end of the interval. That was 0.049. Yeah, good catch. So we are 95% confident the interval here captures the through difference in, make sure I phrase this right, proportion, the true difference in the proportion, no, in the proportion of, or with commonly, I'll just put with white names versus black names. When I say that, remember, it's the proportion of commonly white names minus the proportion of commonly black. Okay. Now that we've got some statistical numbers to work with, we can say it's significant. Does it provide convincing evidence? Yes, no?
What do you notice about all the differences between white versus black? They're all positive. They're all greater than 0. That means all the differences, all the sample differences we got were positive. That means we have convincing evidence. Of a higher fallback rate. For white names. Suggests discrimination. This here just kind of sums up what we did way back early on in this unit compared to what we've done today. So remember, 95% confidence we knew was 1.6 standard deviations away. And we were able to calculate that using inverse norm, which you don't really have to worry about because you'll be able to use a graphing calculator to do all this work for you. Okay. And if it was 80%, well, 80%, it's going to be a smaller, it's going to be a smaller number. If it was 99%, it's going to be a larger number and the interval is going to be wider. 80%, the interval is going to be narrower. So for a T sample, instead of just doing p hat, we have to do p hat 1 minus p hat 2. And instead of just doing this, we have to take this of each one and add them together before square. So putting it all together. Here's the 4-step question. So state. Oh, my notes are incorrect. We are constructing a 95% confidence interval. P hat 1 minus P hat 2. And you have to define both here, where P hat 1 is the proportion of white names who receive callbacks. And P hat 2 is the proportion of black names who receive callbacks. Oh, sorry. Sorry, it shouldn't be P hat 1. It should be just P1 because those are the true proportions. We're doing a sample one to represent the true one. There was something wrong there. That's the plan. The plan is to construct. Calculate. A Q sample. Set interval. For the true proportion of commonly white names minus the true proportion of commonly black names. Were these conditions random? The employers, if you go back to the beginning of the question, sorry, resumes were randomly assigned. Resumes were randomly assigned. It was an experiment. So they were randomly assigned a white name or a black name, and then they were sent out. It wasn't the employers who were randomly assigned. %, we don't need to verify. Okay? Because it was an experiment. I talked about that before. Okay? So you don't need to, whenever it's an experiment, you don't need to verify 10%. Otherwise, you'd have to say, is the sample size for the first group 10% of all in that group, the population, and is the sample size for the second group less than 10% of all in that population? And finally, large counts. Now we've got to find a few here. Remember, we always had to find n times p hat and n times 1 minus p hat. Well, we've got to do that for each group. So we've got to do n1 times p hat 1. And we've got to do n1 times 1 minus p hat 1. And those have to be greater than or equal to 10. And then I'm going to do the same for n2 times p hat 2, the sample size of group 2 times its proportion, as well as n2 times 1 minus p hat 2. So for the first group, the sample size was 2445. The proportion was 0.101. Multiply those, and we get approximately 247. I'm just going to round to the nearest whole number. If you want to decimal, that's fine. So that's well above 10. 2445 times 1 minus 0.101. Now that's going to definitely be bigger. That's 2,198. The sample size for the commonly black name resumes was also 2445, but its proportion we calculated to be 0.067. So that gives us approximately 164. And then the sample size times 1 minus 0.067, which is definitely going to be above 10. it's going to be greater than this, is 2,281. So all greater than or equal to 10. Yeah.
For the first sentence, we're constructing 95% of the that will learn speed at two, and the plan is just to choose.
Yeah. Did I get my notation? No, you're right. I did it again. Yeah, that makes sense. Thank you. My excuse is I got older yesterday, so.
Happy birthday.
Yeah, I just turned 18 plus 40. God, 58. 58, can you believe it? 38. Like, look at this face. 38. Anyway. It was an impressive day yesterday. 58. Anyway. Dude. So, when we did a sample proportion for one sample, we did one prop Z int. It makes sense that if we're doing two, it's two prop Z int. And you will see everything you have to enter on your graphing calculator when you do that. So for the do phase, we're doing a two prop Z int. And we're going to be asked for the following information. The sample size, the number of white names that received callbacks, 246. The sample size of the commonly white named resumes, 2445. The number of black names that received callbacks, 164. The sample size for the black resumes, 2445. And then C level as a decimal, 0.95. So remember, this replaces having to do that confidence interval formula, having to figure out what Z star is if it's not 95%. This just does it all for you. And we're not going to get exactly the same because there'll be different rounding going on between the two ways we did it, but they will be very, very close. Like, what did we get when we got 0.01586? Here we got 0.01803. Very, very close. Same with the second. And then finally, the conclude. Hey, do I get a cookie? Do I get a cookie? Perfect. Anyway. See, like I'm getting old. My mind's just strained. Pretty soon I'd be opening the window, yelling at you, "Get away from there, you kids." Pull my pants up to my chest and complain about the government. We are 95% confident. The interval that we calculated. 0.01803. 0.04905. Captures the true difference. In proportion of callbacks
for white versus black resumes, and that's white minus black. Actually, I'll do it like that, for white minus black resumes. And just like we answered before, draw a conclusion. Do they differ? Yes. Because all of the differences remember that's white minus black. Are above zero. Okay, so you can see very close to what we did for confidence interval for one proportion.